Assalamualaikum and good evening to all of you. So first of all, I'm sorry because I cannot present my research in live because I have another event, AKNC Anjung Seri Budiman. So the title of my presentation is a 3D point cloud filtering algorithm based on weighted eigenvectors in principal component analysis and region classification. Okay, so these are the list of authors for this project. Okay, my student Farah Izzati, me, Dr. Suhaila, and also Dr. Norma alias from UTM. Okay, so this is the outline of my presentation, introduction, some literature review, result and discussion, and also conclusion and recommendation. Okay, so what is 3D point cloud? It is a group of data point in 3D coordinates. Okay, usually it is represented in X, Y, and Z. So the use of the point cloud is to describe an object external surface, and we can obtain the data from various data sources such as laser scanners, photos, and also videos. So what is denoising? So noise refers to the unwanted data that degrades the image quality. So the 3D denoising is a part of 3D point cloud processing. Okay, it is to remove outliers and also to produce a high fidelity output. Okay, so besides, the 3D denoising can be used to preserve the geometry sub-features. Okay, so what is the motivation for us to do this research? It is to preserve the important features because while we are denoising the 3D point cloud, okay, so we need to preserve the important features, and then we will use the weighted PCA introduced by GIA 2019, and we want to improve the method by GIA by introducing the weighted eigenvectors, which is introduced by Salaria in 2020. So this is the framework. Okay, first we will do the data acquisition, and then we will put some noise. So it is called as data corruption, and then we will do the denoising process, regional classification, and also the performance analysis. So this is the data acquisition, the 3D point cloud. Okay, so in this research, we use the box, Stanford Bunny, and also pipe curve model, which is available, free data available in the Point Linet database. And originally, this data does not consist of any noise. It is in 3D format. Okay, and then since each data set consists of 100,000 points, which a usual laptop cannot carry, so we reduce the data to 5,000 points randomly. Okay, and then we do the data corruption, which is include the noise into the data set. Okay, so we are using the Gaussian noise given by this one, W equals to S plus N. So actually this is XYZ. Okay, and in Gaussian noise, we can choose the percentage of the noise that we want to include. Okay, so this percentage will move the original point to a new position. Okay, so the larger the percentage is, the further the point will move. Okay, and then after the data corruption, so we do the region classification. Okay, so this is to differentiate the denoising method that is suitable for a certain region. Okay, so we use the normal vector. Okay, so the region will be split into flat and mutant, and for flat region we will use median filtering, and for mutant region we will use bilateral filtering. Okay, so first of all, we calculate the principal component analysis, or called as PCA. Okay, so the normal PCA used by a lot of authors is given by this one. Okay, but we use the weighted PCA introduced by GIA. Okay, so C here is the covariant matrix, P here is the mean of the neighborhood, and PI here is the data point. Okay, so for weighted PCA, the matrix C here now is called as CW, where W is the weight calculated by this formula. Okay, and then from the matrix C in the previous slide, we can calculate the eigenvectors and also the eigenvalues. Therefore, this research use weighted eigenvector where the obtained eigenvector from the matrix C previously, okay, will be multiplied with some weight. Okay, so the reason for these weighted eigenvectors is to lower the effect of the normal. And then the weight of the eigenvectors is between 0 and 1. Okay, so next step is the region classification. From the obtained eigenvalues from the matrix C, PCA matrix C, okay, so we can use this equation of sigma to calculate the sigma P for each data point. Okay, and then we will use this data to classify based on the sigma value whether that point belongs to the flat region or belongs to the mutant region. In this case, the blue points is the flat region and the red points are the mutant region. Okay, and then the denoising process is done separately between flat and mutant region. Okay, so for flat region, we will use median filtering. Okay, again, this is an improved median filtering. Okay, so this is the formula of median filtering. Okay, so the number of data points before and after the denoising process is still the same. Okay, in our case, we use 5,000 points. So originally we have 5,000, and after the denoising, the number of points is still 5,000 because the definition of denoising in this research is moving the position of the point to a new one. Okay, so this is the new position, this is the old position, and we will plus with a project mid, which is the distance of the sampling point P moving along the normal vector n. Okay, and for mutant region, we will use bilateral filtering. Again, the purpose or the process of the denoising is we need to move the noise to the some position, which is it should improve the representation of the data. Okay, so this is P new is the new position. It is P the old data plus A. So A is given by this equation, and then these are the parameters inside the equation. Okay, again, bilateral is to smooth the mutant, and median filter is to smooth the flat region. Okay, so for result and evaluation, we are using two parameters, actually three: the mean, delta, and also the processing time. So the mean represent the average distance between the resulting point and also the ground truth, which is the original data without noise. Okay, and then this is after resulting point is a point after denoising, and delta is average angle. Okay, if d is the distance, delta is angle, and also we consider one more parameter, which is the processing time. Okay, so since we have three data set, okay, so this one is for box. Okay, so as we can see, we have three columns here. Okay, the last column is all PCA, meaning that we use PCA without weight. Okay, without weight. And GIA here is the weighted PCA, and the GIA salaria is the weighted PCA plus together with weighted eigenvector. So this is what we did in this research. Okay, we improved the GIA by introducing the weighted eigenvector, and we call that one as GIA salaria. Okay, so the highlighted cell here represent the best value. So as we can see here, the best performance, okay, are given by the GIA salaria, which is the method proposed in this research. Okay, the weighted PCA plus the weighted eigenvector. Okay, we use different KNN, which is the K neighborhood. Okay, and then we also use different variable, a different parameter B, which is in the bilateral. Most of the best result are the GIA salaria, okay, which is the method proposed in this research. Okay, this is for the box. Okay, and then we also tested on different Gaussian noise. Okay, and still GIA salaria give the best result. Okay, so this is for box model. Okay, next we have Barney model. Okay, so similarly, Geocelaria give the best performance for all KNN, for most KNN, and also for different variable B, and also the different percentage of noise. And also for pipe, okay, Geocelaria, okay, most of the best values given, most of the best result given by Geocelaria, okay, with different KNN, with different value of B and with different data percentage. Okay, and then we also tested with using the different eigenvector weights, okay, R just now. So R is between 0 and 1. So in this case, we compare R 0.25, 0.5, and 0.75 for this value of B and KNN equals to 1, and the noise is 2.5%. The purpose of this comparison is to analyze whether the bigger or the smaller R will give us the best result. And then from this table, we can see that the smaller value of R will give us the best result. Therefore, it shows the significant weighted eigenvector that is that introduced in this paper. Okay, so um, we should lower the effect of the normal vector in 3D denoising. Okay, so for the conclusion and recommendation, okay, so this research has improved the normal estimation, okay, by using the weight of eigenvector. And for future research, okay, maybe we can consider other features such as color and also geometric data. Okay, so that's all from me. Okay, if you have any question, you can freely contact me through this email. Okay, thank you.